Into the third phase of the trilogy. It's Return of the Jedi. Here we go. Where's Yarrow? Okay. Okay. So I want to talk about 2D magnets, which are, getting very popular. It's very nice. And a little bit about magnetic proximity effects in those systems. We've been talking about spin-orbit proximity effects. There's been yesterday some talk about magnetic proximity effects with TMDs. And we'll address that a bit here as well. So this is the outline. There's going to be 4 topics. So one is 2D magnets and magnetoelectronic devices. Okay. The second will be epitaxial films of 2D magnets and room temperature ferromagnetism. And third will be magnetic proximity effects. We'll talk mostly about the ones in graphene. And then finally, point defect induced magnetism, which maybe we'll get to that. We'll see how the time goes or not. And then after that will be Ahmed's talk on point defect induced magnetism. Really some nice things. Okay. So, but I'm going to start with a prelude for students because there's a very famous theorem about 2D magnets called Merman-Wagner theorem. So it's good for students to know this. Okay. And I hope I do a correct job of it. Okay. So here's the prelude. So we're going to, the theorem is like there's no magnetic order in a 2D Heisenberg magnet at finite temperatures. Right? At 0 temperature, it's okay. And what that is we'll have spins on a 2-dimensional lattice, and the spins can point in any direction in 3 dimensions, so in x, y, z. Okay? And the Hamiltonian is just you take nearest neighbor spins and you do a dot product, and with a minus j, which is the exchange constant. So if j is greater than 0, the low energy state is the ferromagnet. So all these, spins will want to be lined up parallel in order to minimize this energy. Okay? And then, of course, if you have some temperature, then it's the free energy you care about, and then it's possible that it will not order, or at least at some temperature it's going to disorder, right? So the thermal fluctuations could destroy the order that you have at t equals 0. So this is the theorem, okay? Okay, so, well, in addition to, let's say that your ferromagnetic, they're all lined up, you also have these excitations called spin waves, which look like this. So they're normally pointing up, but if they can tilt a little bit and then precess about that sort of equilibrium direction, okay? And if you look at it from the top, you can sort of look at the projection, and then here is one full wavelength, okay? And then you could just, write that in terms of a wave number, which is k over 2 pi over lambda of the wavelength. And then you basically have 2 ingredients for the theorem. One of them is the Magnon dispersion, which the frequency goes as the wave number squared. So that could be like a homework assignment for a student. Okay. You just take the Hamiltonian and you Fourier transform it and take the nearest neighbors. You get 1 minus cosine of k times other stuff, and then the cosine has the squared. So it just works out. Okay. And then the other thing is that this, these at the quantum limit, there's our magnons obeying Bose-Einstein statistics, because you could have more than 1 magnon per mode. And the number of magnons obeys the Bose-Einstein statistics here. And if you plot this number of magnons for that mode as a function of frequency or energy, you notice that as you go to like lower energies, this distribution starts diverging. And so there's the chance these low energy modes, well, they may be heavily occupied. And if you have like lots of magnons, it could sort of shake everything up and destroy the magnetic order. So this is the idea of the Merman-Wagner theorem. Okay. All right, so we can do some, just calculating. The total number of magnons at temperature T is you just basically say, well, tell me the number of magnons in a given mode of wave number k, and then you just integrate over all modes. And then it'll be ddk, where d is the dimensions. D could be 1, 2, or 3, right? And if you go back here, we don't worry about up here because it's sort of exponentially suppressed. We just worried about near zero. Okay, we're really worried about near zero. So what we can do is have the low energy modes where the energy and frequency is much, much less than kBT, the thermal, right? And then so you could expand this exponential into 1 plus the argument. The ones cancel off, then we'll take this other stuff out. But mainly you just have this denominator is the frequency, which goes like k squared. So we can now do the calculations for like 1 dimension, 2 dimensions, 3 dimensions, right? So we'll do it for 1 dimension. So I just take that. So the dk in 1 dimension is just dk, and then the k squared is k squared. I can integrate 1 over k squared, it's negative 1 over k. And I just look at the lower limit where we're worried. So the lower limit is, minus negative 1 over 0, which is positive 1 over 0, or infinity. So in 1 dimensions, you have infinite number of magnons. So infinite number of magnons is like bad news. It means like that's fluctuating, you destroy all your magnetic order. Okay? Unless its temperature is 0, so temperature 0 will make the number of magnons to be 0 and you're saved. Okay, and even it's, even better than multiplying by T. Okay, 2D. Okay, now your D2K is like 2 pi K dK. Okay, that's the element. And now one of the powers of K cancel, so it becomes 1 over K. You could integrate that as a natural logarithm of K. And if you look at the lower limit at 0, you get negative natural log of 0, which is positive infinity. So in 2 dimensions, you get infinite number of magnons, thus no ferromagnetism unless T is equal to 0. Right, so this is the Mermin-Wagner theorem here. But it seems like this is a bad trend. Will it ever work? And it works in 3D, okay. Right, so 3D, this momentum element, the d cubed k is 4 pi k squared dk. I hope I didn't do this wrong. I would be embarrassed if I got these phase factors wrong, or angle factors wrong. But then the k's cancel, and I just got to integrate dk, and so that's just k. And then at the 0 limit, it's some finite number. So there's a finite number of magnons, so the ferromagnetism can be thermally stable at a finite temperature. Right? So 3 dimensions is fine. And 2 dimensions, it's like not good. And then 1 dimensions is very bad. Okay, so this is like the essence of the Mermin-Wagner theorem. Now, but you do have magnetism in 2 dimensions, so there's a way around this theorem, right? And the way around them, okay, so one's the statement. Ising model, these are spins that can only point up or down. They cannot do this kind of precessing business. They cannot do this spin wave stuff. So in the case of the Ising model, there's no magnons. And then so physically, this corresponds to having a really strong uniaxial magnetic anisotropy. So it just points along one direction, up or down, right? And of course, this model was analytically solved by Onsager, so you know that there is a finite Curie temperature, so it's all good, right? And then they don't have magnons, and that's why everything's consistent, okay? And then the other thing that I think, okay, so I'm asking any experts in the audience, in magnetic thin films of metallic varieties, higher order magnetic anisotropies can stabilize ferromagnetism. And I would guess in the 2D magnets, this is also likely to be true, but I don't know if the paper exists, and if it does, I would really love to know it. Okay, but one would expect that this should happen as well. Okay, yes? Oh, please. Oh, microphone.
I kindly ask you all of you to wait for the microphone to reach you. The talks are being recorded, that's why.
Oh dear.
For all of Brazilian students, maybe worldwide even. Everyone, right?
Outstanding. So the question is, so there's a flaw in that theorem. It's not a theorem.
Oh, what's the flaw? Is it dipolar stuff or what?
So this is the Kosterlitz-Thouless transition. So
yeah.
There
okay.
is, okay. Are you going to comment? Okay.
Sorry. Yeah,
so
I forgot.
just as a comment, then
okay.
there is also another
Yes.
weakness, which is that you do have this Kosterlitz-Thouless transition at finite temperature for the 2D systems.
Correct. Thank you. Yeah, I forgot to put that in here.
Would you call that a flaw? Because it's just that it's classical and the other one is quantum. I think it's two different. Well, it's a theorem for the Heisenberg type Hamiltonian, which is quantum, and then the costless Thales is classical. So I think you know it's just two different things, no?
Well, the theorem is just for the three-dimensional spin, right? And this other stuff's for two-dimensional spin, right? No, it's not. Okay, then I don't.
Well, no,
I thought it was. I thought it was for XY.
No, the costless Thales certainly the XY model, classical. It's a vortex, anti-vortex, binding and anti-binding, but that's classical. And the Mermin is as far as I understand, it's quantum in 1 and 2D. Right. So, and what you did is just to show that the fluctuations destroy long-range order.
Yeah.
And that's the same when you have graphene, and people would say pristine graphene should not exist.
Yeah.
Any kind of sort of long-range order in 2D would be
correct.
Forbidden.
Correct. Okay, so that was our prelude. If anyone can help me on bullet point 2, I would really like that. I don't know if it's true, but I'd like to know. Okay. Okay. All right, let me talk about 2D magnets and magnetoelectronic devices. So I want to start with, this is, there were a pair of papers, came out in Nature a couple years ago. This is out of the Berkeley group. And they looked at CGT, which is ferromagnetic in the bulk, and they exfoliated it down. And at least the experiment went all the way down to 2 monolayers, and they used magneto-optic curve effect microscopy. And they can sort of see, here's the bulk curve, and here is exfoliated, 5 layers, 4 layers, all the way to the bilayer. And we can see there is still ferromagnetic, but the temperature, the ordering temperature, the Curie temperature is going down, okay? And then they also developed a theory. So Steve Lewis on this, and they developed a theory about how the Curie temperature should change as a function of thickness. And I will just mention what's going into this theory is actually the magnons. So they talk about the magnons in the monolayer, multilayer, and bulk. And so the magnon distributions are different, and this claims there's a gap. So if you look at this system, it has coupling here. It has some anisotropy, which is the A, and then it has Zeeman, right? So a little bit of anisotropy. Anyways, this is opening up a gap, which allows the ordering to be stabilized. And so in terms of the magnons, you're actually pushing away these magnons that could destroy the order out to higher energies. Okay, and that's how they describe this. And based on these type of calculations, they're able to get a sort of a theoretical curve. And this is the experimental curve. Okay. Sort of back to back with this work is one by University of Washington group, Xiaodong Zhu. This is monolayer chromium triiodide. They have many different thicknesses, and they also use a magneto-optic Kerr effect. And they're able to look, and this has a very strong out-of-plane anisotropy, which gives you a nice square loop. And this is in the monolayer regime. Okay. What's here? And something that's really interesting that came out of the initial study was that if you look at the monolayer, or the bilayer, or the trilayer, well, at least these first two, because as you go to more beyond that, it actually gets more and more complicated. But if you look here, you have a top layer and a bottom layer, and you have this flattening off at 0. So here, the hysteresis loop has a 0, the Kerr rotation has a 0, and that's signifying that the 2 layers are anti-parallel with each other. Okay, so that's why they cancel off. You apply large enough field, it breaks this layered antiferromagnetic coupling, and then they both point in the positive direction, so you get a positive Kerr rotation. If you put a large negative field, you'll break this antiferromagnetic layered coupling, and then they become parallel, but downward. So this kind of curve is a sort of very characteristic shape that, for example, was seen in magnetic metal films a while back. Right, but this is very nice. Okay, and then what can you do with this? Quite a number of things. So one of the things that was done was actually to do electrical control of the magnetic ordering, especially controlling this antiferromagnetic, layered antiferromagnetic coupling. Was this ionic liquid? Do you know? I can't remember if it was ionic liquid or if it was, no, it's not? Silicon oxide, okay. Okay, got it, yeah. So here, what's really neat here is there's a couple of things that are going on. Now, this is at 0 applied electric field. Now you're increasing the electric field, and there's some business where the 0 and the vertical direction is changing, so they're sort of depicting it as maybe the moments are a little bit off. But I think the more interesting aspect about it is the switching field, that where you get saturation. So it actually gets pushed out to higher values. So this corresponds to making the antiferromagnetic coupling stronger and stronger. And there's even some special fields here, like negative magnetic field here, where if you look, it goes into this parallel state at 0 voltage or 0 electric field. But then as you apply more voltage, now you get into the anti-parallel phase. So going from parallel to anti-parallel at just this field. And you could do it at the positive field as well. In this case, it's parallel. And then right here, it switches down to anti-parallel. So what we have here is electrical control of the antiferromagnetic coupling. And on certain conditions, you can actually use it to electrically control the switching of the magnetization. So these are really interesting things that I think people who study magnetic thin films and magnetic systems, layered magnetic systems, being able to electrically control materials is very attractive. Right? So one of the themes that we've had is, right, what's good about 2D materials? Ability to gate, control by electricity. And another is to control like by proximity and so forth, because they're very thin. So a question here.
This scheme for applications is that it requires magnetic field.
Correct.
And we don't want to use magnetic field in, high density devices.
Correct. Yeah.
So it's nice to have a switching without Joule heat losses.
Yeah. You would like to have like a spin orbit torque or something like that, which is 0 field and better in a lot of ways, right?
I have a question.
Yeah.
Don't you want to use magnetic field? What's wrong with magnetic field for this kind of systems?
It's not for these systems in general. One does not want to use magnetic field because it's not possible to generate magnetic field on some nanoscale. So that's why, that's why a decade ago people started talking about all electrical spintronics. Yeah, it's impossible to generate local magnetic fields in some kind of circuit with thousands of transistors, memory elements, and stuff like that. Yeah, so it's nice for the lab, but not for realistic application.
Yeah, but there's always, if you're really clever, you might be able to create some kind of, like, I don't know, an exchange bias or some kind of proximity field possibly that will act as that. So instead of having external field, maybe it could be internal. So I think there's, like, not a complete showstopper, but definitely you would prefer not to have to, apply a very precisely tuned field to your system. Yep. Oh, yeah, these are all sort of low temperature as well. So these are below 50 Kelvin. Okay, and so this is a demonstration of the switching. So we're at either those special positive or negative fields, and then you can ramp the electric field. There's some hysteresis with the electric field ramping, but you can see it's going from like near 0, which is anti-parallel, to larger negative value, which is they're both pointing down, or they're both pointing up, and then you apply a field, and then they're anti-parallel. And so for this positive one, you could just sort of show how reproducible you can do this, so you can go up and down, so you can go back and forth, and go from up to down, and that's what you see in the red curve. Right? So this is pretty nifty, I would say. Yeah. Okay. There was also, I think there's a lot of analogies to activities that are done in, metal magnetic films. And so there's a material that I like is iron germanium telluride, FGT. It's not at room temperature, but it has a very nice out-of-plane hysteresis loop, which is not here, but it will show up in a future slide. It has very nice perpendicular magnetic anisotropy, nice square loops. And this is a magnetic tunnel junction where these two metal magnets have a boron nitride tunnel barrier spacer. So this is the structure here. And so it's basically in the ferromagnet, you have a different density of states for spin up and spin down, majority and minority. If you have them parallel, this big density of states will go into the other big density of states, and you have a lot of conductance. So that's a low resistance state. If you, and just imagine this small d goes to 0, so make everything simple. But if you imagine that if they're anti-parallel, this big density of states will have nowhere to land here. So it's going to become a high resistance state. All right? So this is the typical tunneling magnetoresistance. And it's observed in this system with 2 metal ferromagnets and a tunnel barrier. And I don't know the temperature this was done at, but it's in the paper. Okay? Then there was another set of papers that all came out close together. It's a bit different too. So it's similar. You use graphene. So various groups, Xiaodong, Pablo, Morpurgo, Sen. You know, you basically take bilayer chromium triiodide, which is naturally anti-ferromagnetic. Okay, and then you put in graphene as the contacts. This is a very air-sensitive material, and then you just measure the current. The tunneling current, essentially, on a bias. Okay? And what's really different about this, I didn't mention, but the chromium triiodide is insulating, right? Whereas the FGT is conducting. So this is an insulator, so it's more like a spin filter tunnel process. Okay? So one thing you can see first is, again, this kind of square loops. Not square loops, these kind of anti-ferromagnetic loops with the flat in the middle. You can look at the IV characteristics, and you see they're highly nonlinear. They're really flat, and then they turn on, because this is a pretty big tunneling structure. You have the van der Waals gap in between. You have the ferromagnets themselves, which insulate. So it's a pretty insulating structure. And then there's a turn on. Okay? And the point is, the purple curve is in no field, right? The anti-parallel state. There's a turn on that starts off later. And then the other curves, the red one, for example, is one where they're oriented out of plane. So that's the red one. And then the green one is in plane. So they're parallel but in plane. And it seems like out of plane and in plane are not too different. But the point is that when they're parallel, it allows the carriers to go through, because you're filtering once, and then the second one, once it's filtered, it could get to the second layer nice and easily. So the red and green curves are much stronger in terms of current. And so you can take one of these conditions and then just do a hysteresis loop. So you can sort of see, here's a low current state when it's anti-parallel, and here's a high current state when it's parallel, and that's what you expect. And you can look at the ratios, and right here where it's the turn on, where because of this nonlinearity, you end up having the largest effects, right? So whether it's in plane or out of plane, high field, okay, you get a large increase in your conduction, and you can sort of see that all up here. Right, so it's really sort of taking advantage at some level of this nonlinearity to have a good signal. Okay. Okay. So I'll pause. So these are talks about a lot of exfoliated materials. Okay, I think these are, they're sort of doing analogs of what's been done in magnetoelectronics, and some interesting characteristics, although most of it's lower temperature still. Okay. Okay. All right, so I'm going to...
Questions?
Yeah, are there any questions? It's a good time. Yeah.
Is there some possibility, like in dilute magnetic semiconductors, to have carrier-mediated magnetism? Because what Branislav was mentioning was been done, electrical control of magnetism gating that has been started in 2000 already in magnetic semiconductors and then transferred to metals. And if there is some carrier-mediated magnetism, then there are lots of opportunities how to manipulate these structures. Then maybe their importance would be in themselves. Right now, this doesn't seem to be the case. The importance of these 2D magnets comes from some heterostructures. By themselves, maybe they are not as interesting.
Yeah, I think there's a lot of interest in, essentially dilute magnetic semiconductors or point defect induced magnetism. We'll hear some new results in the following talk. Yeah, there's a lot of, say, density functional theory calculations of various, magnetically doped systems that could be ferromagnetic, and they should be gate tunable. Yeah. Tell me. Yeah.
It's still on archive, I think, but people were doping with the vanadium, the tungsten dicyanide, and they could see up to room temperature.
Yep. Okay, so let me tell you about some work that's been happening on various epitaxial films, not just exfoliated materials, right? Epitaxial films and also systems that go up to room temperature, right? So I think for applications, you'd want that. I think in generally it's nice to have. So this is a work that I really like. It's one of the first intrinsic ferromagnetic materials. It's FGT. This was grown by MBE, by Fa Xiansu. He's in China. And so this is the structure of FGT. There is germanium and then 3 layers of iron and then flanked by tellurium on the outside. It grows very nicely. And the hysteresis loops are very good. So you can sort of see at low temperatures, it's nice and square. It goes up, to about a couple hundred degrees, So it's a very nice, even if you imagine like what kind of material would you just want to have to do some studies. Out of plane, that's at the monolayer level or a few monolayers, integrated into devices, if you want a conductor. I mean, this is like a really nice system. And I didn't mention, yesterday there was some references to some spin orbit torque. I believe it's done with this type of material. I think. Right, thank you. Yeah, with platinum, yeah. There's a new version of it, which is a very iron-rich version of it, which pushes up, you have more iron, it pushes up the Curie temperature. I don't have all the curves from the study, but it's a bulk, it gets exfoliated down to be pretty thin. And then here's some magneto-optic microscopy. And you can see these are out-of-plane hysteresis loops. In the bulk, the in-plane is a bit stronger than out-of-plane. But the probes that they use, this is the Maguire and Xiaodongzhu and so forth, are sensitive mostly to out-of-plane. And there's anomalous Hall effect measurements as well that show some hysteresis, even like up to 270 or so. Right, so this is a variant of FGT. I think it's interesting. There is epitaxial films. One is vanadium diselenide, and this is a result on graphite, VSC2 on graphite. They have these nice triangle shapes. I think probably that's important because there's lots of ways it can grow, but if you get triangles, there's a chance that you can see these kind of ferromagnetic hysteresis loop. This is MBE grown. It's at room temperature ferromagnet, and the magnetization is in plane. There's monolayer manganese diselenide. This came out of my group. These are squid measurements. This is the raw data, and this is the process background subtracted data. This is grown by MBE. It's room temperature ferromagnet, and the magnetization is perpendicular. This is a material that doesn't exist in bulk, but is epitaxically stabilized. So we think it's good. I will mention we've been doing some studies in collaboration with Jay Gupta at Ohio State. So I remember we had a conference on 2D spintronics about a decade ago. That's when I met Yarrow. This was in Singapore. It was great. Just like this meeting is really great. I'm really loving it. And I remember Masashi Shiraishi, and I told him I have a dream to do spin polarized STM. And he was like, oh. And there was various people who said, oh yeah, I was into that, and I think it was Ron Jansen that was his PhD, and he's like, I survived that. I will never touch spin polarized STM ever. and Shiraishi was like, postdoc kokoroshi, meaning postdoc killer. Right? I was like, oh man, this is what I'm going to do. So, so this is some of the first data that we had gotten. And what I'll tell you is what you need in the scanning tunneling microscope is to have a spin polarized tip. It's chromium. You have to make it nice and clean. And then you calibrate it on a chromium 001 surface. And the topography shows these atomic steps, which is very nice. And then if you go from, and basically it's a layered antiferromagnet which goes from one direction to the other, and so forth. And so if you go from one terrace to the other, you expect the magnetization to reverse. So you go and you take some point spectrum. So you sit there and then you ramp the bias voltage, turn the feedback off, and then you can sort of see that the curves look different for the red and the blue. Okay. And then, so you just pick one of the features. So we picked 100 millivolts. And then you just do a map of the surface at that bias. So it's a DIDV map. And what you can see is that it's alternating between bright and dark. So that's precisely what you expect for a layered antiferromagnet. So this indeed is the spin contrast. So you do the spectrum, you try to find a good place, and then you want to map it out. Right? So this is like beautiful. And I'll show you some very preliminary data. So we got this working. We started measuring a different system, and that other system took hold of the STM for half a year because it was generating great data. So this is still preliminary data, but this is manganese diselenide that was grown on bismuth selenide. And the step height is about 6 angstrom, which is manganese diselenide. And we just have point spectra here and there. We don't yet have images, but we hopefully will get this in the next couple of months. Right? So, but the thing to notice is you put in a 1 Tesla minus 1 Tesla out of plane, and then you can see the curves are different. And the question is this sort of systematic? You know, every point is going to look a little different, but you can sort of see some regularities where you start seeing the blue peak a little bit ahead at lower energy compared to the red, and that's sort of regular in all of these guys, right? So, and we've also looked at the substrate and other islands which are not manganese diselenide, and we don't see the spin contrast. So we're really confident that what we're seeing is a magnetic signal, and it's just a matter of, you know, doing the imaging to really convince ourselves. But I feel like very, very good about this. So this is very preliminary. So, and we're unlikely to publish this work, so it's okay. But we'll hopefully have a much more comprehensive and thorough studies of 2D magnets studied by spin polarized. Yeah.
Could you just say briefly the motivation to put manganese selenide on the topological insulator?
Yeah.
If you can say what is the motivation?
Well, there's always going to be 3 motivations on systems like this, right?
Okay, just this. If you can just say.
There's 3.
I'm just
There's
curious.
3. There's like 3. There's always going to be the 3, and all systems that are kind of like heavy metal. Well, no. So one is proximity effect for topological states. That's one. One is spin orbit torque, right? Okay. Right. Heavy metal, and one is skyrmions. Okay. So those are always like the 3 that people want to do. Okay. And if you didn't know, now you know.
Okay.
It's not a big secret, I would say. But
it's not like anisotropy or ferromagnetic anisotropy would change. Do you expect that?
It definitely could change.
Okay.
It definitely could change, like because whenever you have a high spin orbit couple, I mean the anisotropy comes from the spin orbit coupling being strong. So if you have anything that's in contact like high spin orbit, then that could affect the magnetic anisotropy. Okay. So if you had like the say interfacial or proximity kind of spin orbit, that could definitely affect the magnetic properties. Mm-hmm. I think that would be very exciting. Okay. Like yeah, for sure.
Thank you.
Yeah. Okay. All right. Okay. So I do want to talk a little bit about magnetic proximity effect. It was touched on a couple of times. This is some work that we've done. We've done it in collaboration with Michael Flate here. So this is what the magnetic proximity effect is, or it's also called proximity exchange interaction, or some people like calling it induced ferromagnetism. Okay, I don't call it that usually. But the idea is you'll put graphene on top of some magnetic material, and typically we like insulators because we'll want to do some transport or optical measurement. And it's really an exchange interaction of spins in graphene or whatever 2D material you have, with interactions with them, with those electron spins, with the ferromagnetic moments. And it generates an exchange splitting, E sub EX, in the conduction band of graphene. So if you just look at this Dirac cone here, you have a Dirac cone, then if you have a proximity exchange field, in this case, since the magnetization is in plane, it'll be like a proximity exchange field that's in plane. And what it's doing is it'll create a splitting of the 2 Dirac cones. So one will be for spin, say, along the magnetization, and the other will be spin opposite the magnetization, and and then there'll be a splitting, and you can convert that to an equivalent magnetic field. Okay, so it could be 10 Tesla, 100 Tesla, 1 Tesla, 0.1 Tesla, who knows? Okay. And yeah, so okay, so there's a number of reasons why people would want to have ferromagnetic proximity effects. Okay, we'll leave it at that. Okay, here's the works that I know about in graphene. There may be more. These are the work that I know about in TMDs. I might not be completely accurate here. I don't have the references. They were there yesterday. But they've been observed in both systems. I mean, I think in the long run, these will be very important type of interactions, both the proximity spin orbit, proximity exchange. Okay, so there's this idea, which I think is cool, is if you could sort of electric field control spin precession in graphene, or just the exchange, induced exchange splitting in any 2D material. In some materials, they won't precess because there's a strong internal spin orbit field. But the idea is that you can have your carriers, and with an electric field, if it's like a thick enough material that they can move a lot, you can, like if it's an up electric field, that'll bring the electrons down. And it'll put it into intimate contact, meaning the sort of quantum mechanical contact, right? So you get a wave function overlap of the carrier with the ferromagnet. You can get a large exchange field, and in this case, in graphene, it could cause it to precess, right? And in other cases, it'll just cause a big spin splitting that you might detect optically. On the other hand, if you apply the opposite electric field, then the electrons will be pushed away from that interface, and then you have a small wave function overlap, small or zero exchange field, and little or no spin precession. So this, in spirit, this is really similar to the spin orbit valve transistor idea, where you push the carriers close to the heavy metal, the TMD, or further away. So like the very start of today. Okay? So it's this idea of combining proximity with gate tunability. So this is something that you can do in principle in 2D materials. Maybe you can't do it in other materials so well. Okay. Okay, so this is some results from Jingxi's group with graphene on YIG. It was like the first report where they see anomalous Hall effect signatures of the proximity effect. There's a work with graphene with europium sulfide based on Valley-Zeeman effect, where they have signatures of the proximity effect. And for us, we wanted to use an approach using spin transport to detect spin precession based on the proximity effect, proximity exchange field, right? So this is the idea of the experiment. And so we've talked a lot about precession in the first tutorial. So the idea is, you know, we're going to inject some spins into graphene and detect them on the other side using this non-local spin transport scheme geometry. But the difference is it's going to be on top of a ferromagnetic insulator substrate, which is YIG, yttrium iron garnet, right? And then if you have it parallel, they will make it across. If you have it perpendicular, now this exchange field will cause precession, which leads to dephasing, and these spins should not make it to the detector. So this is like the on state, and this is the off state. So that's the concept of the experiment. And I'll just show you the primary results. Okay? Oh, good. So this was out of Van Wees' group. So they got this working first, and they did it in monolayer graphene. And so the idea is here. It's on YIG. You apply the magnetic field, and you rotate it around. And then the magnetization, it's a very soft magnet, so it will follow the applied field. These cobalt electrodes will not rotate because they're not as soft, and they have shape anisotropy and so forth. So they're relatively fixed. And what you can see is that when you are 0 degrees, which is perpendicular to the spin orientation, then you get a minimum in your spin signal. Whereas if you are at 90 degrees, and so you're parallel to the spins, you get a maximum. So this is this kind of spin modulation that you expect to get from the spin precession. And then, yeah, if you have a longer channel, then you have more distance and time to precess. So you start seeing a pinch off over here. It's going from the on state to the off state. We've also done this, and we did it in a bilayer graphene. We were thinking maybe we'll want to start gate tuning this. But we see a similar kind of curve where you can sort of see in our, well, we have a different axis, but 0 is the YIG magnetization is parallel to the cobalt. And then you rotate it 90 degrees and it's pinched off. Spins are pinched off, I guess. And then now if you go 180 degrees, it's maximum again, and then it comes back down. Yeah, so this is a complete spin modulation you get in just a couple of microns. Yeah, so this is a very nice spin modulator, and it's all based on like proximity exchange field. Okay. I'll pause there if there's any questions regarding anything before. Okay. Okay, good. So I'm going to go into the very last topic. Point defect induced magnetism in 2D materials. So this is a topic that's gone a long. Oh, you have a question?
I lost your talk about if you have the magnetic field in plane, why is the energy is splitted? Oh, yeah, why energy is splitted? Yeah, you have the figure.
Yeah.
Previous more.
Here.
No, not previous one. But yeah, one more.
Okay.
Yeah, one more. Yeah.
Okay.
Yeah. Look like it here.
Yeah.
So you have the in-plane magnetic field. Why the energy is splitted?
Oh, because it's like the spin of the electron has overlap with the spin of the magnetic moment in the yig, so like the iron typically. And then there'll be a S, S dot S, like the spin of the electron dot spin of the iron, say, with some constant in front, like J or something, some exchange constant, right? So that term looks like a magnetic field, right? And then then you have a magnetic field energy S dot B, and that's like a Zeeman splitting. So in the end, it looks like a Zeeman splitting. Yeah, sure. Okay, good. Okay. So, wow. I'm looking for Oleg Yazyev. I've never met him, but he was here yesterday. He's here. Maybe he'll be at the excursion tomorrow. So I've shown his data like dozens of times, and I never actually met him. And he gave a talk yesterday, and I was like, "Oh, this is Oleg Yazyev." No idea what he looked like. What do you mean? I don't know. So I want to talk about magnetic moments from point defects. So this goes towards your question about dilute magnetic semiconductors and so forth. There's different kind of point defects. One is transition metal impurities, so you could just put those in, and then the question is, will they couple, by carriers or however. Another is other types of point defects that are not transition metals, like hydrogen or vacancies, right? And so this is a prediction that was made for graphene. So there's work on graphite and some studies, but then this is maybe, this is one of the early papers to look at defect-induced magnetism in graphene, which here's a location of hydrogen, and here's a vacancy. And you can sort of see, regardless of which one, there's a couple of features that are nice or consistent, is that it's not actually that we're looking at the hydrogen, but we're looking at the spin polarization inside the graphene. So it's actually creating this kind of alternating spin polarization. So red and blue are opposite signs. So it has this kind of alternating spin polarization that lives inside the graphene. And you can also see that here. And that's just sort of a general feature. And then it's possible that maybe these dilute magnetic moments, they can be paramagnets, which are fine, or they could maybe have ferromagnetic ordering. And also there's a lot of interest these days in point defects. They can be used potentially for quantum information science, spin qubits, single photon sources and such. Like actually there's a lot of work right now on hexagonal boron nitride for single photon emission, right? And there was just a paper recently that did some optically detected magnetic resonance, and it seems like it has some spin character to it, right? And so what's really interesting about those systems, again, is gating and proximity. I mean, that's what you can do if you could get a real handle on the 2D materials. So there is a nice study. This is done by Irina Grigorieva. And what they did was they took graphene, these laminates, and fluorinated them with different amounts, and then measured these in a squid, and then fit them with Brown functions, and found that there's a spin 1/2 paramagnetism, right? So I don't, Yaro's the expert on fluorine and hydrogen. I don't want to make any comments right now because I'm not up to date on this. But I think that this is the similar variety to what is happening in hydrogen, okay? There's some experiments that we ourselves did where we took our spin valves, which we're used to seeing now, this parallel, anti-parallel stuff, and we said, maybe we can use this as a way of detecting magnetism, right? And this is like the whole story here. So inside a vacuum chamber, we pump it down, and then we drop down atomic hydrogen, right? And the idea is that if there's an exchange interaction between the carriers, the conduction electrons, and these localized moments that are predicted to be created by hydrogen, then they should induce some spin relaxation, and we should be able to detect that. So when we put on a certain amount of hydrogen, we see a dip, right? And this was just after this workshop in Singapore, where I met Yaro. I had never met him before except for seeing papers. And I was like, wow, what's going on? What's going on? And we had talked about things. I said, okay, I think there's a story here. And so we conversed. And actually, it can be explained, the data can be explained pretty well as in a fluctuating exchange field model. So the idea is that there's a bunch of moments, and then the spin is going to go through and sample them. And the spin has two interactions. One is an interaction that's an exchange interaction with this magnetic moment, and the other is the Zeeman term, applied field, right? And you could just sort of cast this interaction as an exchange field, but since you're hopping from place to place, it's a time-varying exchange field. And we know that, I didn't know actually back then, but I learned that a fluctuating magnetic field can induce spin relaxation, and that problem had been solved in terms of Diakonov-Perel spin relaxation, right? So we utilized that machinery, and then we're able to explain our data. So this was quite nice. But what could be even better is to get even more direct if you can do scanning tunneling microscopy. So this is Ivan Bruega's beautiful studies on scanning tunneling microscopy on graphene, and then you put individual hydrogen down, and then if you do the spectroscopy, you can see, so this bottom line here is just graphene by itself. You put the hydrogen atom, so if you're on the hydrogen atom, you see two peaks. And theoretically, you can calculate what those two peaks might be. And here is showing that one is a spin up and one is a spin down. So it's like sort of this exchange split doublet, right? So this is showing that, you have sort of a magnetic moment right on the area of the hydrogen. So I find that to be quite nice. And then you could do even a little bit more. You can take two of these and you could position them. And what's nice is, you can't maybe see it here, but you can sort of see there's sort of like this triangular shape. So depending on if you're on same sublattice or opposite sublattice, this like three lines will come out in the opposite three directions if you're on the other sublattice. So you kind of know where you are. And so if you put two hydrogens and you drag them close to each other so that they're on the same sublattice, then your magnetic moments are on, you say, okay? But if you drag them somewhere where they are not on the same sublattice, then they're turned off. Okay, so this is the idea. So the magnetic moments are on when hydrogen's on the same sublattice. The magnetic moments are off when they're on different sublattices. And this is like one of the things that in all the theory papers I've read, people agree. Same sublattice, I take that back. Never mind, I take that back. But this is the typical. I see a different paper in my head, so. But this is the typical behavior that most of the theoretical papers predict. Okay, and the point is that you want to have a ferromagnetic coupling if you are getting the same sublattice. There might be some differences of opinion if you're on different sublattices, but when you're on the same one, people agree, and you're pretty close. That's ferromagnetically coupled. Okay, so how do you get on graphene to get on the same sublattice, right? Monolayer graphene. Though both sublattices are the same, But it turns out if you have hydrogen on bilayer graphene, the two sites are not the same. One we call the alpha, which will be beneath it is another carbon, and beta beneath it is an opening, the center of the hexagon. Okay, so they can be different. And I think, you know, Palacios, maybe some of these folks had the first ideas about this, and we thought we would try it out. And when we did these kind of studies, we basically put on hydrogen for a certain amount of time, and we measure the resistance. And then we put a little bit more, we measure the resistance. And of course, the charge neutrality point shifts a little bit, or actually quite a bit. So we just measure we measure it as a function of gate voltage with respect to charge neutrality point. So this charge neutrality point gets lined up. And we see the emergence of a couple of extra peaks. One is this peak, which I'm calling the beta peak, and this other peak, which we call the alpha peak. And then my students were hunting around trying to understand what goes on and found Yarrow's paper, which I didn't cite, but it's there, from 2017 or 16 or 17. And they calculated what is the energy spectrum of the resonance scattering if you have hydrogen on top of the alpha site. And this is what he got, something like this. And what if you put it on top of a beta site, and this is what he got? They look quite different. So just purely from an electrical measurement, you have a chance to tell what's your occupancy of your alpha sublattice versus beta sublattice. So even without doing, like, say, STM measurements, you can gain a lot of information. So first of all, that was really surprising to us, because we have done all these kind of studies on monolayer graphene. But the problem with monolayer graphene, I guess by symmetry or some reason, you end up having the peak at 0, so it just coincides with the charge neutrality point, so you don't really see it. But in the bilayer graphene, they exist as separate peaks. And so with this kind of method, we can actually do annealing studies, and we found at certain temperatures, the hydrogen starts disappearing from the alpha peak, and you have primarily occupying just the beta sublattice. And in principle, that should induce ferromagnetism, right? But we haven't done that measurement yet. So this may be a future, I don't know, spin polarized STM kind of study, maybe. I don't know. We'll see. Okay. But what about ferromagnetism? Is it possible? Yes. Oh, yeah, question. Yeah.
I just want to understand what you're plotting there. That's an experiment, right? Yeah.
Oh, here, yeah.
So you're just increasing the hydrogenation time. Why is it shifting?
Correct. Probably some charge transfer. So it's doing some electronic doping. So it shifts to the left, which means it's becoming the graphene's getting more N-type. So the hydrogen are kind of acting like donors.
So the hydrogenation time essentially says that you're going to be having more hydrogen, say, on the beta side.
Correct.
Or on the alpha side, right?
Correct.
Right. So that they both become maybe a little bit more visible. Well, the alpha peak certainly.
Yeah,
right?
yeah.
The beta is still not quite there.
Well, but it's a lot smaller as well.
Yeah, sure.
Yeah. So
and the shift you're saying is just charge transfer in.
Well, I mean, it's a shift of the overall curve. So when you look at the raw data, you'll see this curve, and then you'll see the blue one will be over here, and then the light blue one will be out here. So we just like sort of shift them to sort of collimate all of the charge neutrality point peaks.
Mm-hmm.
Yeah. So actually, if you look really closely, the beta peak comes out first.
Right.
Even though it's smaller, and then you don't see the alpha one until a little bit further. And so the calculations are that the beta site should be a little bit more thermally stable than the alpha site. And so that's consistent when we're depositing, and it's also consistent when we desorb. Yeah.
And just maybe I should ask that to Yarrow actually. What would control this shift in the theory? You have an idea?
I think we should give the word to Dennis here. It was his calculation, so he should be visible here.
Yeah, we have time. I only have a few more slides, so it's.
Yeah, so what was the question?
3 or 4. 3 or 4.
No, I would say that in the theory, you simply see that you are shifting the Fermi energy, so it comes from the T matrix calculation, and you will see that you are having a self energy due to the interaction,
So effectively, your Green's function is energy minus self-energy, and this is doing the shift. Is the, let's say, simple answer.
Yes.
Is it possible to apply a weak magnetic field to see if the magnetic impurities are responding to that, to have a kind of final proof?
Yeah. We don't. You mean like to see magnetoresistance or?
Yeah, but I mean, I guess that in your experiment, these impurities are paramagnetic, right? It's unlikely that you are only populating one of the sublattice. So if you, I don't know what is the energy scale. I mean the scale of the magnetic field to align them all, but that might be. I mean the resonance might be stronger. I don't know. Or in case of a ferromagnetic ordering compared to a paramagnetic ordering, I don't know. But this is also a question for theoretician.
Yeah. So I think. I mean, we don't have enough field to polarize them. I mean, we don't have 0.1 Tesla, but in principle, we could do a spin transport measurement. In principle, we could do a spin transport measurement. And it should reveal it, but they got really tired.
Actually, actually, I just remember one paper we published where we found an anomalous suppression of quantum interference when you have long-range ferromagnetic ordering. That is, all these hydrogen impurities are populating one of the sublattice. So for some reason, the other sublattice that is preserved is offering channel for ballistic transport or whatever you like, and there is a signature that we have predicted. So that's what my question actually was related to that, but I just remember now.
I see. Okay. All right, so there is ferromagnetism. This is work out of Columbia, Tomo Uemura. So yeah, they actually start seeing in MOTE2 and MOSE2, hysteresis loops, field cooled, zero field cool, hysteresis loops. There's some ferromagnetism here. And then they do some studies. This is by Abhe, Pasupathy in that group. And then they see a couple of defects, and they ascribe them, one to molybdenum vacancies. The molybdenum vacancy is over here, sorry, it's on the right. And then this one is molybdenum substitution, so molybdenum going onto the telluride site. So I guess they must have done some density functional calculations and done a match. Okay, so that's one thing here. Oh, there's some vacancy-induced platinum diselenide. Next talk by Ahmet. Okay, he said, please talk about point defects. Okay. And so this is after the trilogy is done. I have some closing thoughts, which is just this. It's been a while studying spins and so forth, and various aspects of magnetism, and so forth. And now it's like an amazing time. Actually, you have graphene, which of course has spin transport, and this Dirac structure, which is topological in nature. There's the TMDCs, which have strong spin-orbit coupling, which can be very useful. There's Valiant spin optics, and it has Berry curvature, and probably the magnets, some of the magnets have Berry curvature as well because of the structure. And then now there's magnets, which can be as memory elements, spin polarization, proximity exchange, and I didn't talk about it all, but magnon transport could be interesting as well. And what's nice about the 2D material system is they're very highly tunable, both by interface, also by electric fields, and to generate not just highly tunable, but sometimes even new properties altogether in van der Waals heterostructure. And when you really start getting down to it, the nuts and bolts, you really want to understand the effects of proximity and gating, all at the atomic level. We have really clean interfaces. And the type of areas where they could be important, scientifically or applied, I guess you could say, one is the tunable magneto-electronic devices, so that's the natural thought. There's topological states in various ways. There's TMDCs that are topological. Graphene itself is inherently topological. If you put enough spin orbit in exchange, you should get all sorts of states. There's also optospintronics, which I think is an emerging direction. There's been a lot of optical work in TMDs, also interfacing with magnets and graphene. And this is a nice light matter interface, so converting between photons and electrons. Finally, if you go to quantum limit, you know, point defects even, right? You can really start looking at single photon emission and even spin qubits. And it's just a matter of control. And the advantages that you might be able to get with 2D materials is just the high degree of tunability that you don't get. It's much more than in most other materials classes. So I feel like, you know, I opened up this whole trilogy with this statement, and we've seen a lot of talks really oriented towards this direction. And I think it's a very, very exciting direction forward. All right, thank you.
So we
We're out
don't
of
really
time.
have time for questions. Maybe one very quick question, if there's still something that you want to clarify. Okay, I think we have had
there are many
several
questions
questions and discussions already.